Okay, so let's make a start of ST2334. So this is lecture group 2. So all the lecture notes, and materials, question sheets, so on and so forth are on this new system, LUMI-NUS. And this course is essentially almost identical in content to the other 2 lecture groups. The notes are the same, it's just a mild variations in the delivery of the notes. So just some logistical details. All this information again is on this alumni source system. So again, this is this I guess group 2. So we're in LT26 today, LT28 tomorrow, 2 to 3:35. And I guess the registration for tutorials is already done. But if you're doing manual registration, please go ahead as usual. Okay, so the minor things here. So first of all, office hours. So if you want to come and see me, you don't understand some part of the lecture notes or tutorial information, you can you can come to my office at 4 o'clock on Thursday, which is in S16, block S16, 0402. Okay. If you have got a timetable clash, you can send me an email. We can schedule another meeting, or if you prefer, you can try and resolve your question over email. Okay, so the 2 major points of interest. So the assessment, the main point about the assessment, so this is the same assessment for everybody in this course, the other 2 lecture groups. So you have a midterm, which is, we're trying to schedule for the 9th of March, which is a Saturday. The reason being Saturday is you've got a huge group. The material is very clearly marked. So there's chapter 3, section 4. That's what you have to revise for. It's worth 30% of your final grade. The setup is 10 multiple choice questions and 3 longer questions. Okay, that's the same for everybody, the same 10 questions, the same 3 longer questions. The standard, the format is 1 hour. You're allowed a cheat sheet, but it's closed book. Okay, so it's a closed book examination. So this is consistent across the final exam and this midterm closed book, but you have a cheat sheet. Okay, I think you get a calculator as well, non-programmable. Okay, so that's the first thing. So there's no take-home assignments. This is just one midterm. So the examination is again 2-hour examination, 5 questions, non-programmable calculators, closed book, cheat sheets allowed. It's pretty much in the same style or level of difficulty as the previous semester. Okay, so the lecturer for last semester is the same as this one. He's doing one of the groups. So we're doing the same course, so you can use that to practice from. Okay, and it's 70% of your final grade. Okay, so those are the assessments. Please don't send me an email asking me, do we have a midterm or what is the exam? The information is here, and this information is on your online materials. The lectures are video recorded, so if you don't like coming here, you can watch it on video later. So then, just to finish off, just very quickly, so problem sheets, there are 11 non-assessed problem sheets. They're already on available. You can look through them and try and do them if you want. There are some solutions already on them, and there will be full-typed solutions as we come to each tutorial. Okay, so those are all the logistics. Hopefully it's pretty straightforward. There's nothing really too difficult to understand. Again, if you send me a question about the midterm or the exam with this thing here, if information is not here, then I'll answer. Otherwise, I won't. It's just that you've got 200 people in the class, and it's hard to answer questions which you have the answers to. Okay, so what's this course about? Well, it's probability and statistics. It's probability and statistics 101, essentially the most basic way you can learn probability and statistics quantitatively at the undergraduate level. There's 7 chapters. Okay, so like you might understand that we would hope to be roughly up to chapter 4 by the halfway point of the course, and so these are several topics of which you may or may not know what they are yet. The basic idea is to give you a notion of what is probability, which provides you a calculus or a kind of set of rules for which one can hope to do real-type statistics, that is data analysis or applications in practice. And there are a variety of topics. We're going to see all of them as we go along. Okay, so if you want some set text, if you like reading books, or if you want to look at something to read around the subject, these are the 2 recommended texts. You should be able to get these pretty easily, at least the e-versions, I hope. they're pretty straightforward books along the same lines of the course. Okay, so that's that. Hopefully all those details are pretty clear. If there is something that's not covered here and you don't know what to do, just let me know. Otherwise, we'll continue. We'll start. Okay. So these lecture notes, they're not my lecture notes. They're Dr. Chan's notes. They're the same lecture notes as last semester for the people who took this course, if anyone did. The first chapter, so the thing to keep in mind for all of you is that some of this material for me, I find it relatively straightforward. So if I go too quickly, let me know, because otherwise you're not going to understand what I'm doing, and nobody's going to get anything out of the course. So this first chapter is just the basics of probability, which are basically, what is that? Well, it's just the underlying rules, if you like, or axioms, which allow one to construct uncertainty statements about experiments, okay? And that's basically what we're going to think about or learn about in this chapter. Okay, so there's an overview for the course. I think that this chapter, I think that the main things that we want to think about are basically these first two things. That's what we're going to talk about today, which is some introductory concepts into the notion of probability. So these first three sections, there's never any mention of what is a probability, okay? These are all kind of preparatory type of ideas which allow one to construct distributions over random events. So the idea is that we have some underlying phenomenon. We want to make uncertainty statements about that phenomenon, and we want to kind of form a way to do that. And that's what we're going to learn about, because that allows us to do more interesting things. Okay, so these are the two things that we're going to cover today. Basically the notion of what is a sample space, I'm going to tell you what that is, and some operation of events. This is basic, so for those of you who study some mathematics, the second section is all about essentially set theory, okay, but it's not really at the level where one would study in a math course. Okay, if we get time, we'll look at these counting methods. And there's a lot more topics here, there's too much to take on board right now. But really, if you want to think, if you're interested in reading ahead, if you like reading ahead, basically this is where the probability gets going, and axioms of probability. So if you have a textbook or if you have some sort of online material, that's the place to start reading from, if you already know these kind of basic things. Okay, very good. So let's begin. So this is a pretty gentle beginning to probability and statistics. So the notion is, well, there are two notions here you can see on this slide. The first of which we're not going to see very much of for now, which is the notion of an observation. Okay, so this is what I'm talking about, this thing here. And basically that's the recording of information. So in statistics or in many other disciplines, you have some sort of phenomenon which you're interested in measuring on, predicted on, estimating, so on and so forth. And we refer to that as an observation, which is almost always, it says numerical or categorical, but if you're more inclined, you could say that's continuous, discrete. It could be a vector, it could be a matrix. There's a lot of things it could be. But for us, we can just think of those as being numbers of some kind. Okay, so for example, you observe the value of the stock index in S&P 500 every day. That would be a notion of an observation. Okay, and the objective is ultimately to use these observations to try to make inferences about the real world. Of course, we're a long way from being able to do that, but that's really where we're trying to head towards. Okay. Now, the main things are really where this parts of these notes really start, or the concepts that we think of begin, is the notion of an experiment, a so-called statistical experiment. What we mean by this is some sort of physical or computational or something like that experiment where the underlying outcome is intrinsically non-deterministic. I don't know what's going to happen. For example, the most obvious example is rolling a die or flipping a coin or something like that. Intrinsically, there is some deterministic procedure which underlies this, but it's so difficult to understand that we cannot do that. And what we're trying to do is to understand or to assign some sorts of mathematical understanding when no physical understanding is available. Okay? And so this is the notion of a statistical experiment. All it is basically some procedure which is going to generate observations, if you like, but it's basically something which we don't understand very well and is going to provide us some sort of notions for which we want to make probability statements about. Okay. So associated to this is a sample space. Okay, so basically you have the collection of all possible outcomes of this experiment. Okay, so for example, and I think we'll see an example very soon. Yes, that basically it's all basically everything that could happen. Okay, and as you might imagine, as we go on, we'll try to understand the chance of all things possibly happening. That will be 1 because probabilities will be numbers between 0 and 1. Okay. So this is the first thing to keep in your mind. So the first thing is the notion of the chance, or the collection of all things that could possibly happen, and that's called the sample space. So let's have a look at some examples of what the sample space could be. Okay, so the first one, again, these are not my notes. If you don't like the language, don't complain to me. So the first example is rolling a die. I don't know, you could call it tossing a die if you like, but if you can roll a die. Okay, so a dice, if you don't know, is a 6-sided object with the numbers 1 to 6 on them. When you roll them, it lands upwards on one of the faces, and one of those faces reads 1, 2, 3, 4, 5, and 6. Okay, so assuming the dice lands, we're hoping we're competent enough to achieve that, then the collection of all possible outcomes would be that it lands 1, 2, 3, 4, 5, 6. Okay, and this is an example 1 of an experiment, and 2 of the case the collection of all possible outcomes. Okay, so that's that. So here's another example. Okay, if you're only interested in the scenario, right, you could also evaluate this experiment in a different way. So my experiment, the way of evaluating it, was I was only interested in the face value that the dice took when it lands. But you could also think about the sample space of only being interested whether or not that is even or odd. So the most obvious example of where you'd be interested in this at all would be some sort of game or betting experience, for example. So even odd would be another collection where I'm only interested in these two outcomes. Okay, so another example, those are kind of, you can imagine there are a lot of examples in this course, is the scenario where you roll 2 die. Okay, so again, if you're just interested in the face value of dice 1 and the face value of dice 2, then basically there are, of course, 6 times 6, 36 possible outcomes, and those outcomes would be 1 and 1, 1 and 2, 1 and 3, 1 and 4, 1 and 5, 1 and 6, and so on and so forth, until you get 6 and 6. Okay, and that's the collection of all possible outcomes in this experiment where I'm interested in the face value of dice 1 and dice 2 when I flip them both, I roll them both, excuse me. So another example is hopefully this will be pretty clear at the end of this, is the experiment which consists a little bit more complicated this time. You flip a coin, okay, so a coin which could land head or tails, assuming that we designate those two values to the flipping of the coin, and then you only flip it again if you get a head, otherwise you roll a dice, okay? So here now you have a different set of possible outcomes. What could happen here? Well, first of all, if you flip a coin and you get head, well, you can then get a head again or you can get a tail, okay? And so these two scenarios here, S, which is the sample space, and those 2 points, HH, what that means is, just in case you're wondering, although it seems fairly straightforward, is that this refers to the outcome that you first flip a head, and then because you flipped heads, you flip the coin again, so you get a head. This one, well, this one is where you flipped a head, and again, if you flip a head, then you have another chance if you want, if that's your thing, and you can get, in this case, a tail. Okay, so they have to be distinct. They can't be the same outcome. Of course, the same outcome is not reported twice. It doesn't make a lot of sense. In the second scenario, what you can do is you flip the coin and you get a tail. And if you flip the coin and you get a tail, the outcomes now, well, what happens is in this experiment is you now roll a dice. Okay, and if you roll the dice, of course, you can get 1, 2, 3, 4, 5, 6, and these are these 6 possible outcomes which are associated with the chance that in the with the event that the first flip of the coin it results in tails. I don't like example 4; it doesn't make a lot of sense. So let's move on to example 5. Let's have a look. So example 5 is again another example. So it's a kind of classical example from probability theory. We won't be seeing too many of the theory, but we will be seeing examples. So this is basically, you've got a box. It's got a blue ball, a white ball, and a red ball. And basically you put your hand in, you take out a ball, then you put your hand in again, and you pick out a ball. So there's no replacement, okay? And in this case, if we label the possible outcomes as W for white ball, B for blue ball, and R for red ball, then in this is the set of all possible outcomes. You can get a blue ball and a white ball, a blue ball and a red ball, a white ball and a blue ball, and so on and so forth. Okay, so basically you start with B and you think about the other ones, because there's no replacement here, so you really only have, once you've taken one out, you can't choose it again. Okay, very good. So that's, hopefully that notion, I think that notion is clear, right? You have an experiment, you're interested in it for some particular reason, maybe you're not interested in any of those experiments, but you may be in something else. And the first step into being able to introduce the notion or concept of probability is to understand everything that could possibly happen. And in our case, everything that possibly could have happened is summarized precisely by a discrete collection of things that could happen, okay? To kind of add this, or to exemplify this, we kind of look about this, the notion of a sample point. Now, a sample point is simply an element of the sample space, okay? Well, I said it exactly, I didn't even read it. What does that mean? Let me see, we've got examples. So what that means is the following, okay? So again, so here we have our sample space in our urn example, if you like, or drawing of balls, okay? And basically a sample point is a point in an element of the set, okay? So here BW is an element of S, okay? Okay, so so what you say here, so for example, if we go back to example 1, what was example 1? Well, it was the notion of rolling a dice. Okay, so you could get 1, 2, 3, 4, 5, or 6. So a sample point is a singular element of the set 1, 2, 3, 4, 5, 6. Okay, so here we have the sample point 1. Okay, so it's a member of the set S, okay, for those of you who like math, okay. As a second example, so our second example was a subset. Again, we rolled the dice, it could be even or odd, right? So an element of the set, even or odd, is even or odd. Okay, that's an example of a sample point. That's a single position, a single element. That's what we mean. Our second example, if you've already forgotten what it is, like I have, the second example was where you roll 2 die. Okay, so you get 1, 2, 3, 4, 5, 6, 1, 2, 3, 5, 6. Okay, and so this was our sample space. It had a wonderful 36 elements. And as you can see, for example, one sample point would be where I get a 1 and a 1. Another example would be I get a 6 and a 5, or a 6 or a 6. Okay, but when I say sample point, to make it clear, it's just one element. Okay. So our third example was you flip a coin. If it's heads, you flip the coin again, or if it's tail, you roll a dice. Okay, so that gave us the sample space: heads, head, tail, tail 1, tail 2, tail 3, tail 4, tail 5, 6. So the sample points could be head, head, or head, tail, or tail 1, tail 2, so on and so forth. Okay, so and so yes, and so then finally our urn with balls in it. We take the ball out, we take another one out. The ball is blue, red, or white. Okay, so this was the collection of all possible things that could happen when we draw them out of the urn or the hat or whatever you want. So one example of a sample point would be BW. I could take WR, I could take RB. All of those positions of those two values, those two letters, which lie in S, are sample points. Very good. Okay. So we've covered, I hope, something which is relatively straightforward so far. We have an experiment. We think about all the things that could happen. In our world at the moment, we can do that. And we think about individual things that could happen. So we roll a dice. It could be 1, it could be 2, and so on and so forth. In order to really, this is what we want to do now, is to try and think about not only individual things that can happen, but particular subsets of the sample space or events that could happen. Okay, so an event is a subset of the sample space. Okay, so let me give you, so you can see the notes in front of you. Let me just give you some graphical thinking here, just to stop your. Keep you a little bit more interested, or maybe not so. The idea basically is you have, if you think of this as a square, can we see the square? No, we can't. It's not very clear either, is it? Okay, so the square you can think of being as the sample space. Okay, so here's a continuum, but we've been thinking about discrete things. Okay, and so what we're going to be interested in ultimately is thinking about what is the chance that some part of the sample space happens. Okay, so this is a shaded region. And so this shaded region we'll call a set A. That's supposed to be A. Okay, and that set A is basically trying to summarize quantitatively what some possible part of the experiment is, and we'll ultimately try to assign the chance of that occurring. Okay, and that's really what we're talking to. If you don't really like the words, that's intrinsically all we're trying to do. Okay, this diagram is, you'll find that anything that I write here will not be particularly exciting. It's just to try to illustrate a little better what it is I'm talking about on those slides. Okay, so returning to our notes, let's have a look at some examples. So an example of an event, okay. So here we take example one. Example one, rolling a die. I get number 1, 2, 3, 4, 5, 6. So we could think about different things. So I could think about the chance, or I could think about the event that I get an odd number. So an odd number would be 1, 3, or 5. And so that would be an event, okay? An event, note that a sample point is an event, but an event is not a sample point if you want to think of it that way. The event that you get a number greater than 4, well, that's a set, and that's a set of values 5 and 6, okay? And again, if you're, for example, if you're interested in rolling die, or you use it for something more interesting than just thinking about probability, you may be interested in these events for some reason. Okay. So again, here's an example where where a sample point is an event. So here, if you have in our second example, remember we were 1b, you roll a die, and you're only interested whether it's even or odd. Well, remember, odd is a sample point, but it's also an event. Okay. So events contain the collection of sample points, but sample points are not events. Sample points are events, but an event is not a sample point, sorry. So let's have a look at example 2. So again, that was rolling a pair of die. You get 1, you get 2, you get 3 on 1, or up to 6, and so on and so forth. Okay, so now here's something that you may be interested in. So the sum of the die is equal to 7. Okay, so some of you might know a bit about dice games, and then that might be a score you're interested in. So this particular event, we're calling the event A. It's a set. Okay, this is the notion of a set. So for example, if I roll a 1 and 6, 1 plus 6 is 7, and so on and so forth. So for example, here 5 and 2 is 7, 6 and 1 is 7, and so on and so forth. Okay. Note that we do not repeat things. This is there's only one scenario where we're only rolling it once. So I get 1 and 6, and that counts 1. Okay. So our third example, you flip a coin if it's heads, you flip again, otherwise you roll a die. Okay, and so this event here is the chance that is the summary that no die is thrown. So in this case, this event is basically summarized by the fact that basically I roll a head and I could get a head again, or I flip a head and I get a tail. Okay, so this is another event, and at our kind of level of understanding, the event is just a collection of sample points. Okay, so our fourth example was the one where you had the urn, you put your hand in, it's a blue or red or a white ball, and so on and so forth, and I put it in again and I get another one. So here the event A is the white ball is chosen. So in this scenario, of course, there are several chances that could, several scenario where that happens. This one, this one, this one, and this one. Okay, and they're transferred here between those positions. Okay, and then in tossing 2 coins. Okay, yes. Okay, so if you flip 2 coins, you can get the sample space, of course, heads, heads, head, tail, tail, head, tail, tail. Okay, so here are some potential events of interest. You get no head, or 1 head, or 2 heads. Okay, so no heads, well, that would be basically this case. 1 head, well, this case, and 2 heads would be this case. So it says getting no head or one head, or two heads. Okay, so these sample points satisfy one of these three constraints, at least one of these three constraints. If you look at the second example, this is, again, it's an event. So the event that you get no head or one head. Okay, so here you get no heads. Here you get a one head. Here you get one head. Okay, this phrasing is critical. It's or. Okay, if it said and, if this thing said getting no head and getting one head, that's obviously something that can't happen. And the event, there's a mathematical way to describe that. It's called the empty set. Okay, that can't happen. We're going to talk about that in a moment. Okay, and this is the event getting two heads or getting two tails. So here I get two heads and here I get two tails. Or, okay. Okay, very good. So that was the notion of an event. So you had an event, we had a sample space with a sample point, and we had an event. And a simple event is basically an event if it consists of exactly one outcome. So as I said a few moments ago, a sample point is an event, but if an event is not a sample point. So the scenario where the event corresponds to one particular outcome, you get, i.e. a sample point, the event is said to be simple. Okay, so that's, did we see an example of that? So here, this was an example of that, and we're going to see a few in a moment. And a compound event, excuse me, so it's just terminology. We need to know what these things mean because we're going to use this language freely as we move throughout the course. It's compound if basically you have at least two outcomes, or one or more outcome. Okay, that's one or more sample points, so you have 2, 3, 4, so on and so forth. Okay, so let's have a look at the examples. Hopefully these examples, at least they make things clear even if you're not excited about them. So remember, example 1, you roll a dice, you get 1, 2, 3, 4, 5, 6. And we look at the two scenarios, so compound events and a simple event. So the compound event here we look at the case an odd number occurs. So an odd number occurs, the event could be 1, 3, or 5. That's the set 1, 3, 5. It has at least two elements of this set, so it's a compound event. Similarly, if I want to consider the event that we obtain a number that's 5 or 6, or bigger than 4, that's the set 5 or 6. That has two elements. It's a compound event. It's a simple event. Well, that's just, for example, I roll a 6, or I roll a 1, I roll a 2, so on and so forth. Okay. Back to the 1b. So 1b was the summarizing of the roll of the dice where it's either an even number or an odd number. So a simple event is an odd number, for example. Okay, and in this one, it's not a very exciting sample space because basically the only compound event that lies in B is S itself, actually. Okay, so remember then the second example, you roll a die again, six-sided dice. So here one compound event. So A is defined to be the set of it's the set of outcomes such that the sum of the value of the die is equal to 7. Okay, and so again, remember we already know what that is. That's 1, 6, 2, 5, 3, 4, so on and so forth. The number of outcomes in this set is at least 2, so it's a compound event. Okay. If I take a set B, B is different. The sum of the die equal 2. Well, in this case, there's only one case that could happen where I rolled 2 1s. Okay, and that's a simple event. Okay, let's have a look. So the third example, you flip a coin. If it's head, I flip again. Otherwise, I roll a die. Okay, so a compounded event. Well, here, a compound event. One example is that I don't throw the die, okay? So I don't throw the die if I flip a head, okay? And there are two cases, two possible outcomes in this case, where I get a head and a head or a head and a tail. A simple event, one example is I roll a 1. So what that means is, first of all, I have to flip a head, and then I have to get 1 when I roll the dice. Okay, so let's have a look. Let's look at something which is becoming marginally more interesting. So S is the set T such that T is greater than or equal to 0. Okay, what does this thing mean? Well, this is just basically the semi-infinite real line. Okay, so it's a number which keeps on going forever and ever and ever, right? It's like when you draw the graph, it's just the right line that keeps on going, if you like. Okay, and basically this set is supposed to denote the life in years of an electrical component. Obviously, the set S is a bit optimistic in this case. So in this example, we're asked the following. We want to find the event, we'll call it A, okay, that the component fails before the end of the 5th year. Okay, so S is the sample space, right? That's all possible outcomes. So it could fail, well, this one says it could fail instantaneously, i.e. it never worked, or at some point in the future it will fail, and that could potentially run forever if we're very optimistic. Okay, so this event, A, that the object fails, the electrical component fails in less than 5 years, before the end of the 5th year, so T is measured in these units T are in years. That's just the interval or the set T such that T is strictly less than 5 and at least 0. Okay, so it's an interval. Okay, so what this thing means is, just in case you're wondering, again, just to make things slightly marginally more interesting. All I mean, again, if you don't understand what that. All right, doesn't work anyway, it doesn't matter. It's just a line, where the interval is 0 to 5. Sorry about that, for some reason it's not coming on. Okay, so those are the things. So we talked about what? We've talked about a sample space, the set of all possible outcomes. We talked about a simple event, i.e. elements of the sample space, which are points. We've talked about events, which are just subsets of the sample space, and those events which are simple, i.e. elements, or compound, where there are multiple elements of that space. And then we've talked about this notion, well, that's all we talked about really. So let's have a little think about a little bit more. So we're going to introduce two notions. One which is called the sample space. Okay, so the sample space itself, which is the chance that something happens, is the collection of everything that could possibly happen, and it's called the sure event, actually almost sure event, but we'll call it sure for this class. That means that basically something's going to happen, and that's definitely going to happen. There's no doubt about that in our minds. So basically, in our rolling the die, if we roll the die, we expect it eventually to land on a number which is 1, 2, 3, 4, 5, or 6, and that's sure. Okay, we just don't know which one of the 1, 2, 3, 4, 5, or 6 it will land on. And a second point, which is important, which is a remark, I guess, is that a subset of S, which is entirely empty, okay, it's called the empty set in mathematics, and we're going to call it that as well, and it's denoted by this phi. Okay, this is the symbol. It just means that the set contains nothing in it. Okay, that's all it means. So we're going to use that. It's called a null event. Why is it called a null event? Because basically the empty set is something which doesn't contain anything. Okay, so it doesn't contain anything. It's called null because basically it cannot happen. Okay. That's what we're going to think about. I mean, of course, we haven't yet described the notion of a probability yet, but you can see that we're going to lead towards that. Okay, these are just two remarks. Okay, very good. So that's the first thing. So basically, the first section, 1.1, is basically getting us, I guess it's more of a motivation than anything else. It tries to tell us things that we may be interested in making or quantifying from a kind of practical perspective. And hopefully gives us a motivation to want to study section 1.2. 1.2 is a little bit more dry, I'm afraid, but unfortunately it's kind of like the core element of probability theory. So if you want to do probability theory at some level, and we're doing it at undergraduate level, you need to be able to do some operations with sets. Okay, sets are just collections of, we've seen multiple sets. So again, if you're wondering what is a set, so here's an example of a set. Okay, that's a collection of points. Okay, and in order to be able to try to understand events and probability of events and so on and so forth, we need a kind of underlying algebra to enable us to kind of summarize these events. And this is what it is. This is what we're going to talk about. So operation about events. Hopefully, I mean, I think that you used to study this at A level. I don't know if you still do, but anyway, even if you have never studied it, hopefully it will not become too problematic. So we now introduced two notions, which if you haven't seen before, they're called union and intersection. Okay, and it's very simple. They're very simple concepts. Okay, basically, union and intersection at the beginning for us, let's say, is just a statement about two sets, and basically it tells us something about their interaction in some way, depending on whether that operation is union or intersection. Okay, so S is the sample space. It's the set of all possible outcomes. A is an event and B is an event. So these are two collection of values which lie within S. Okay, at least lie within S. They could be S themselves, actually. So our two notions. The first one is the notion of union. Okay, so I'm talking about this thing here. It's page 24. So the union of an event. So we have an event A and event B, and basically the union, which is a specific notation. Okay, so when I say A union B, that's what I mean by union. Okay, A U B. What does it mean? Well, in words, what it means is that the event which contains all the elements which are in A, and all the elements that belong in B. Okay, so basically, if you take a member or a value in A union B, it lies in either A or B, or maybe both, depending on what those sets look like. That is to say, if you want to characterize this mathematically, the operation A union B means I take the collection of values X. Okay, this notation is the set X. I'm going to see if I can get this thing to work again. Why it doesn't work. Very frustrating. Okay. Well, for now, I'm just going to write things on the board. I know they don't come out on video, but don't worry that there's not going to be anything too much different from what you're written here. So if you can't read this, I'm essentially writing something which is almost the same as this thing. Okay, I realize if you're at the back, you can't read this. But basically, what it says is as big as... Oh, good God, the pens don't work. All right, so the pens don't work either, so I can't write anything. Sorry about this. Okay, well, I'll just speak and hopefully you'll find it just as entertaining. So this notation A union B means the set. Okay, so these curly brackets, they mean set. So I take the collection of values X. Okay, these X's are elements of are single points in the state space. They are, if you like, simple events. Okay, and basically this set consists of all the simple events where the simple events belong in A or they belong in B. Okay, there's nothing more than that. Okay, so what does that mean? Okay, so this plot, which is nicely put on here. So here, as before, I wrote that square. That square represents the sample space. That S is the set of all possible outcomes of our experiment, ultimately which we want to describe. We'll suppose that A is this kind of oval shape here, and B is this circle here. Okay. Now, what A union B means, if I take a point in this set, it has to lie in here, or possibly here. Okay, because this point here, any point in this kind of position, lie in both A or B. Okay, so the set A union B, if you want to shade things, and I would like to have shaded things, is all this one and all this one. Okay, and that's all it means. All the elements which are in A, and all the elements which are in B. If you like, it's a kind of set addition. I have a set, I have another set, and I put them together. Okay, and I don't duplicate things. Okay, so that's the notion of union. It's basically adding together elements. Our second operation, if you need to know these two operations to do anything in probability theory, again we have the sample space S, where we're referring to probability. Okay, we have two events A and B, which are a collection, are subsets of the sample space, potentially including S itself. Okay. Now the operation of intersection is slightly different, as you might expect. It has a different name. So the procedure of intersection of two events A and B is basically the collection of values x, right, which belong to A and to B simultaneously. Okay. So if A and B have no common element, the intersection is the empty set. Okay. I don't like this. Doesn't make any sense. This is the notation I will always use for A intersect B. Okay. I highly recommend you never to use this. This notation will not be at all understandable to almost anybody. I've never seen it in my life, and I've been studying probability theory for 20 years. Okay. So A intersection B. Okay, and it's just all the elements in A and all the elements in B simultaneously. Okay, so what does that do? What does that mean? So let's have a look at this example. So if you like, sometimes you might like graphs or pictures. What is the set A intersection B? Well, it's this little bit here, where if I take a point in A, it lies in A, but it also lies in B at the same time. Here, this is not A intersect B, so it's just this little, I don't know what to call the shape, it's kind of like a little bit of a circle. Okay, so they lie those elements in A and B at the same time. If there's no overlap, if there's no event in A which lies in B, their intersection is empty. Okay, so it's not quite a subtraction event. It's not really subtraction, but it's kind of what are the points that A and B have in common. Okay, so I think this is our third. So our third definition, our last definition, you need the complement as well. So there's only three primary operations, and after we can do those primary operations, we're good to go. So the complementation, the complement of a set of an event A. So we have, again, it's important we have a sample space S. We have only one event A. Okay, so I have the complement of an event A with respect to S. So S is our sample space. And we use the notation A prime or A superscript C. Either is acceptable. I prefer A superscript C because A prime, sometimes you have objects which are functions and you use a prime for derivative. But you can use either, whichever one you feel happiest with. I prefer A superscript C. I think in these notes they're A prime. It doesn't matter too much. Okay, and it's all the elements. What is it? It's all the elements, the set of all elements in S which are not in A. Okay, and you can express that symbolically. So that's the set. So A complement, A prime in this case, is all the elements X which belong to the sample space, but they don't belong to A. So what does that mean? Okay, so this is a nice graph, nice plot, excuse me. So here S, this whole shaded blue region, if you can, hopefully it doesn't look blue, but anyway, this region here, S, this rectangle. So this is my set A, which is supposed to be in green. Okay, it's this oval. So the complement of A is this region which doesn't lies outside of the circle and of course lies within S. Okay, and that's basically what they are. So just very quickly a review. So we're going to have a break for 5 minutes. So the way I run lectures is at 1:45 we stop for 5 minutes, have a break, and then we start again. So what I want to say before we have our break is just a summary of three things that we've just discussed. So three things which is basically set operations which basically form the crux of probability theory: union, intersection, complementation. So union and intersection are operations of sets typically concerning two sets. So union, I have a set A, I have a set B, they're in a sample space S. The union of A and B are all the elements which belong to A and all the elements which belong to B. Okay, that's basically just the sum of those elements, if you like. It's not quite a sum. The intersection is basically you take a set A, you take a set B. The intersection is basically all the elements which belong to A and B simultaneously. Okay, and that's what this means. And the complement is basically the event A with respect to a sample space S is all the elements which don't belong to A. And using these operations, we're going to build up a kind of theory for probability, which we're going to see in a lot of examples, you can see. All right, so it's 2:44, at least according to the clock at the back. We'll break for 5 minutes. We'll resume at 14:49. We go for another 45 minutes. We finish at 25:02. Thanks. Okay, so we can please resume. Okay, so let's have a look at some examples. So we're going to look at this page is basically all about they're all about intersection and unions. So we're going to look again at example 1. Example 1 was the notion I roll a dice. I get 1, 2, 3, 4, 5, and 6, or 6. And I think about 3 particular events. My 3 events are A, B, and C, which is the set 1, 2, 3, the set 1, 3, 5, and the set 2, 4, 6. Okay. So let's think about the operation of union and the union of A and B. So I'm looking at this first bullet point. This is page 27. So the union of A and B, what does it mean? It means all the elements which live in A and all the elements which live in B. So let's have a look. Well, 1 is in A, so immediately that's in. Okay. 2 is in A, so that's immediately in. 3 is in A, that's immediately in. Okay. Now if I look at the set B, well, 1 and 3 are already there, so I'm only going to repeat those. And then I have the extra element 5. So the union of A and B, or A or B, is just the set 1, 2, 3, 5. Okay, let's do this. Let's do it at least one more time. So A and B, A union C. So the set A is the set 1, 2, 3. The set C is the set 2, 4, 6. Okay, so just as before, first of all, I put all the elements of A in immediately. Okay, now if I look at C, 2's already there, so I don't care about that. 4 is now going to be added, and 6 is going to be added. And so now the union of A and C is 1, 2, and 3. And the extra elements are 4 and 6, which come from C itself. So our next operation, it's an exciting operation of B and C. B union C. We're still doing unions. So I have the set 1, 3, 5, which is B. I have the set 2, 4, 6, which is C. And I think about the union of B and C. So the union of B and C, first of all, I put B down, so I get 1, 3, and 5. Now 2 is not in B, so I'm adding that to the set. So I get 1, I get 3, and I get 5. Now C, 2 is not in A, B, excuse me, so I put it here. I get to 2. 4 is not in B, so I put it here. And 6 is not in here, so I put it in here. So the set B is 1, 2, 3, 4, 5, 6. And that, of course, is exactly equal to the sample space in our example. Okay, so now what do we do? Well, now we've looked at hopefully the procedure of union is fairly straightforward, at least when you have these type of elementary sets. Now, what if we want to do unions of 3 or more events? Well, it's not very much different. The first thing to say is that if I take A union B union C, it happens to be the case, it's true, and I will state all of these things slightly later on, that if I take the union of A with the union of B with the union of C, that is the same as, first of all, taking the union of B and C together and then creating the set A union B union C. Okay. This is an identity. It's true for any sets A, B, and C, and there's no assumptions made at all. This is just part of the logic of the set theory. Okay, and that operation makes life slightly easier. Why does it make life easier? Well, because we know that B union C the union of B and C is the sample space S. Okay, so now A union B union C, of course, is A union S. And A union S is the sample space. Okay, so give me a minute. So I'll give a. Can we resume, please? Is that okay? Okay, so let's go on. We can also do that the other way around. So A union B union C is the same as the operation A union B I do that first, and then I take the union with C. So we've already done the operation A union B. That's 1, 2, 3, 5. And then we get the event C. So C is so this is now the union of 1, 2, 3, 5 with 2, 4, 6. Okay, so from this, so I get this one and I add the elements 4 and 6, and I get 1, 2, 3, 5 union 2, 4, 6, and that's the sample space. It is the same either way around. Of course, these two events, they're identical and they're equivalent to these two. Okay, so it doesn't matter which way you do the union operation, you're going to get the same thing. It's fundamentally, it must be the case that this one is equal to this one, and if this, that means that this one is equal to this one. Okay, so that's union. Hopefully that's pretty straightforward. What's A intersection B? Okay, so A intersection B. So I look at A, that has the elements 1, 2, and 3. Now I look at the set B. Now what are the elements of B which also belong to A? Well, that's the element 1 and that's the element 3. So the intersection of A and B is the set 1 and 3. Okay? That's intersection. Let's have a look at a few more examples. It's the same scenario. So now I've still got the case where I've rolled the dice. I've got 1, 2, 3, 4, 5, 6. I've got the sets A, B, and C. They're the same. Okay, and I ask the question: what's the intersection of A with C? Well, let's have a look at A. A has the set elements 1, 2, and 3. C has the elements 2, 4, and 6. The only common element, the only common sample point, simple sample point, if you like, is the point 2. Okay, so 2 is a set. It's a set of one point. Okay, so the intersection with A and C just gives you the point 2. Okay, finally, well, not finally, but the last of our easy parts of of intersections of B with C. So now if I look at the set B, that's 1, 3, 5. I look at the set C, that's 2, 4, 6. Well, there's no element in B which belongs to C or vice versa. Okay, so what that means is the intersection with B and C is simply this symbol phi is the empty set. Okay, so basically B and C, if you ultimately we'll talk about probability theory, B and C cannot happen simultaneously. Okay, let's have a look now at the case where you do intersections of 3 events. So just like unions, which are distributive, okay, if you know what distributive means, if you don't know what distributive means, it means this, that basically I can first take the intersection of A with B and then take the intersection with C. Okay, well, A intersection B, we did that. That's the set 1 and 3. Okay, so now I do the set 1 and 3 and I think about the common elements with 2, 4, 6. Well, there's no common elements. So 1 and 3 and 2, 4, and 6, they don't have any common elements. So the intersection of A, B, and C is again the empty set. Okay. We can also mix things up. Obviously, now what we've been doing is we've been doing intersections and unions, where you can do unions and intersections at the same time. So this one asks, what's first of all, the A intersection B? Well, A intersection B, we know what that is, right? That's 1 and 3. And then I want to take C. So I take 1, 3 union with C, which is 2, 4, 6. So now I'm interested in the union of these two. And again, the union of these two is exactly 1, 2, 3, 4, 6. Okay? And you can do a similar event. So you can do similar things here. So A intersection B. A intersection B union C, I can do that again. So B union C, I've worked it out. B union C was the sample space. A was the set 1, 2, 3. So 1, 2, 3 intersect with the sample space is 1, 2, and 3. Okay. It's key. The key point is if I take A intersection S, I get back A. Okay, this is something which you don't have to concern about yourself with yet. I'm going to tell you about these rules as we go along. Okay, but hopefully those set operations with unions and intersections were straightforward. The last one is the complementations, the complement. So remember, A complement is everything which is not in A. So let's see here. So we have an example. 1, 2, 3, 4, 1, 2, 3 is the set A. So the complement of A are the elements in the sample space S, which do not belong to A. So that's 4, 5, and 6. Okay. Now if I take the set B is the set 1, 3, and 5. Okay. Now if I want a complement of B, there's all the elements in S which do not belong in the set 1, 3, and 5, which is obviously 2, 4, and 6. Okay. And we can call that the event C, which is what we had in the beginning. And you can mix complements into intersections, actually. If you want A complement intersection B complement, well, that's 4, 5, 6 intersection with 2, 4, 6. Well, the two elements which are common are 4 and 6, so that is equal to that. And that's actually equal to A union B complement. Okay, that's true in general, and we're going to state that at some point. Actually, this is true in general. The answer is yes. So A union B, what was A union B? Well, if you cast your mind back, it was 1, 2, 3, 5. Okay, where are we? Here, 1, 2, 3, 5. Now I take the complement of that. Those are the elements in S which are not 1, 2, 3, or 5, which are 4 and 6. Okay, and that's true in general. So the question's asked at the bottom of the slide, is it true in general? The answer is yes. Why is it yes? Well, basically that's one of the kind of rules of these set operations. We're going to state those. It's true. There's no proof of it. You can prove it, but we're not doing proofs in this class. The answer is yes, and I'm going to state that later on. Okay, very good. So now we move on. So again, these are all just terminology, basics and basic concepts. We're not learning anything. If you struggle with this, we're going to have trouble later on. So I have two events, A and B. And they're said to be mutually exclusive or mutually disjoint. So we prefer in probability the notion mutually exclusive because it's a kind of more probabilistic type statement. And two events are said to be mutually exclusive if their intersection is empty. Okay, this is basically this, and the statement A and B are mutually exclusive is an exchangeable statement mathematically. Okay, so what that means is that I haven't got any element in A which belongs to B and vice versa. So here's a plot, this is an example. This is a Venn, they call it Venn diagrams. So this is a square, this rectangle is the sample space S. This oval is the set A, this circle is the set B. You can see that no element in A, no point in here, belongs to here, or vice versa. So these two events are mutually exclusive. As I said earlier, mutually exclusive, I didn't tell you what a mutually exclusive was, but what I said is, from a probabilistic perspective, mutually exclusive events have probability 0. They cannot occur simultaneously. Okay, we're going to see another example, very exciting. We still go back to our rolling the dice, 1, 2, 3, 4, 5, 6. A, B, and C, I think, haven't changed. So B and C are mutually exclusive. We already know that because we worked out what was the intersection with B and C. So what's the intersection of B and C? Well, it's the empty set phi, because there's no element which belongs to B and C simultaneously. Okay, so we say precisely that the events B and C are mutually exclusive. But if you look at the events A and B, okay, their intersection is the set 1 and 3, because I have the set 1 here, 1, I have a 3 here, I have a 3 here. So they're obviously not mutually exclusive because their intersection is precisely non-empty. Okay. 1 and 6, obviously, these, if you take these sample points, okay, these elementary events, 1 and 6, well, that's a set which only contains 1 and a set which only contains 6. If I take the intersection, well, nothing in the set 1 belongs to the set 6, so this intersection is precisely empty. So they're mutually exclusive. So just to make a remark, it's an important remark actually, is that A and its complement are mutually exclusive. And it's kind of fairly obvious from the definition if you've forgotten what complement means. So remember that the complement of a set A is all the elements which don't belong to A. So naturally, if I take the intersection of A and A complement, well, what I'm going to get back is the empty set, because I cannot have an element which belongs to A and A complement simultaneously. So A and A complement are mutually exclusive. That's what this remark means here. Okay. And of course, A union with its A complement is equal to the sample space, just in case it's not clear. Okay, so these are the operations of union, intersection, complementation, the notion of mutually exclusive. Of course, we're not necessarily always interested in just one event. We're often interested in multiple events simultaneously. And one can easily extend the notion of unions of sets from one set to n sets, where n is an arbitrary integer, at least a positive and non-negative integer bigger than 2. Okay, so what this thing means in red, so this is going to be, we're talking about the union of n events. So A1 up to AN is a sequence of events. It's a sequence because we have A1, A2, A3. It's not a series, just in case you're wondering. And basically, if I'm interested in thinking about whether something that happens in one of those events or all of them at the same time, I think about the union A1, union A2 up to AN. So it's a union of n events simultaneously. What does it mean? Okay, well, it means it contains all the elements that belong to one or more of the events of A1 or A2 or AN. That's basically all the events which belong to A1, A2, A3 up to AN. Okay, so what we do in practice, we use this notation. It's very important to understand the notations. So this, what does it mean? So this is a big cup. It's a union sign. It's the union from I equals 1 to n. Okay, so it's important to understand what these things mean. So this is the index set. A is subscript I, so I is the index. It goes from 1 to n in our again. N is finite. So what this means is this thing and this thing is exchangeable. This thing is exchangeable. Now what does it mean? If you're not happy about this notation, what it means is this means the collection of points x which belong in the sample space such that they either belong to A1 or they belong to A2 or they belong to A3 and so on and so forth. Okay, I don't think we see it. So basically what you're doing is you're adding all the elements of A1 and A2 and A3 up to get together again without repeating things. Okay. It's just the notion of going from 2 to n, where n is at least 3, 4, 5, whatever you like. Of course, if you can do unions in multiple, you can do multiple unions. You can also do multiple intersections. So the notion of an intersection of n events. Okay, so it's the same thing. So we basically turn those cups to U's, if you like. So A1 intersects A2 intersection AN, and it is what you might expect it to mean. It basically are elements of the sample space which simultaneously belong to A1, A2, A3 up to AN. Okay, so one might expect that if you, for example, you have a set A1, A2 up to AN which are somewhat large in size, in cardinality we call it, then basically the intersection of all those sets is going to be quite small. Okay. So what does that mean? So what is the notation? So here we take the intersection, this big U, if you like. U has gone the wrong way around. So the intersection I goes from 1 to n. So I is the index set, this index set of these collection of events A1, A2 up to AN. And this thing means the same as this, and this is just repeated on the line in front of you. And what it means is, again, if you prefer the mathematical notation, it's the collection of x which belong to the sample space, and simultaneously x belongs to A1 and it belongs to A2 and it belongs to AN. If a sample point x belongs to all of those sets A1 to AN, it's a member of this intersection. Okay, that's what it means. Okay, so as I say, you could start with 2 huge sets or 3 huge sets, but if you take the intersection of those 3 sets, the size of the resulting intersection may be small, relatively. Okay. Okay, so again, let's see. So I think I've got this working. Let me just make sure that you understand this notion of multiple. Okay, it works. So what I mean by this intersection, so here, again, I draw my sample space. Can we see it? Not quite. So if I take A1, A2, and A3, so again, this is supposed, this one on my left is A1, this one on my right is A2, and this is my A3. What the intersection of all 3 sets is just this shaded region here. Okay, that's what it means. Okay, it belongs, the elements of this intersection belong simultaneously to A1 and A2 and A3. Okay, so that's the intersection. If I take the union of these 3 sets, well, that's just all of this region here. Okay, so this is supposed to color in those 3 circles. I wonder, you're wondering why I'm not doing art. That's why, you can see. Okay, so that's basically the union of those 3 sets. Again, whether you take anything from it, but the formal definition is already in your lecture notes. Hopefully that helps a little bit if it wasn't clear. Okay. So it's basically, so by the way, those plots, those graphs that I drew, they're not formal proofs. I'm just trying to illustrate to you what these things mean, not trying to tell you what they mean. Okay, so these are basic operations of sets. So this is basically a set of rules which, if you understand what these rules are, at least if you know what they are, you will be able to do some things in probability. Okay, there is no proof of these events. Some of these are definitions. Excuse me. This is where they've gone to now. Sorry, gone to the end. Excuse me. I got very excited there. Where do I go to? Okay, here we are. So these are a collection of rules which, if we understand how to do them, they're going to make our life very easy. They are, if you want to take it as definitions, you can quite try to question why they make sense. They do make sense, actually, and there are some reasons why they make sense. But if you don't understand why they make sense, it's not so important. It's just understand that they are. It's just like trying to understand that 2 + 2 is 4. It just is the case, although there is not actually a proper mathematical proof of why that's the case and what it means. It's not important for us to know why. Okay, so these are operations which you should understand. And at least know. Okay. And they look dry, but they make sense. So the first one, sorry, I've just highlighted a bit of 2, but I'm talking about the first one, page 34. So the first one is the intersection of A with its complement, and that's the empty set. Okay. Well, we can formally understand why that's the case. Well, it's clearly the case just from the definition. Why? Because if X belongs to A and X belongs to if X belongs to A, X cannot belong to a complement, okay? And therefore, the intersection of A and A complement is precisely empty, okay? And that's actually a word proof of it, right? Because it's true by definition. I can't have an element which belongs to both A and A complement, hence the intersection is empty. Okay, that's operation 1, so that's true. If you want, you can prove that. I can prove that for you on the board. But it's not important to have that. Property 2, the intersection of any event A with the empty set is precisely empty. What does that mean? Why is that the case? Well, the reason that's the case is if I take any element in A, okay, that cannot belong, if A is non-empty, by the way. If it's empty, it doesn't matter. But if A is non-empty, I take an element in A, well, that doesn't belong to the empty set because by definition, the empty set doesn't contain anything. Therefore, there are no elements in A which are common with the empty set. Therefore, the only thing you're going to get for an intersection of a set A with the empty set is the empty set itself. You're going to have to use that at some stage. So I think I mentioned that this one we've already said because A and A intersection, A is mutually exclusive, A and A complement are mutually exclusive. Of course, any set A with the empty set is mutually exclusive. The next one is the property that if you take A and union with its complement, again, what does that mean? I take all the elements in A and I take all the elements in A complement and I put them together. That's going to give you the sample space. Why? Because basically the complement of A is every element in S which do not belong to A, and then I add them on to all the elements which are in A. So clearly, basically, if you're wondering why is that true, and this is not a proof. If you remember when we introduced the notion of complements, A union A complement means I take all of this thing in green, if you can see the green, and I add them to all the elements in this blue, and what I get at the end is my rectangle S. Okay, so A union A complement gives you back the sample space. Okay. So that one is hopefully the first 3 properties are really clear because basically we have discussed these things at some length. So property 4. So property 4 says I take A, I take its complement, and then I take its complement again, I get back A. Okay? So if you prefer, the complement of a set is itself. Okay? Why is that the case? Well, let's use our our graph. I like this graph. It's very exciting. So why is that the trace? So what this operation, so it's A complement. So I start with A. I get A complement. So I start with this this oval if you prefer. That's my A. Now I take the complement. I get this rectangle without this oval. That's my A complement. Okay, now I take the complement again, which is everything which is not in A complement, which is in S, and I go back to A. And so the complement of the complement is the set itself. Again, you can formally prove it if you like. Okay, so that's that. And then you have this last rule. So again, it's a rule. You don't have to understand why it comes from. So if I take A and B, I take the complement. It's the same as taking the complement of A union with the complement of B. You can take that one as being true. Some of these are just, that's, if you like, we could do another graph. But this, again, it's a property. So basically, you take A, you take B, you take all the elements in A, you intersect them with B. So A and B intersect B is just all the elements in A and all the elements of B. And I get rid of them. I get the complement. That's the same as taking the union of A and B complement. And it's the same if you'd flip them around. So here, remember that what you have here is I have A intersect B, and I take a complement, and I go from intersect to union and complement to complement. You simultaneously get the same thing. When you take A union B and take the complement, you get the same thing. Okay, you can check those. Those are kind of very straightforward. Okay, so the last four properties are kind of intuitive ones. They're basically called distributive laws. Yeah, distributive laws. So what does this mean? So the first one says I take A or B and C, then basically I can expand that out in brackets. So what the thing means is that basically I can expand. It's like an operation where I can expand brackets. So again, I'm just going to write it down again. So anything I write is never going to be very deep. But what it says is I take A union B and C. Okay, so if you can't read that, that was just the left-hand side of 7. And it says basically what I can do is I can put this one together and then I can intersect it with this one together. So that means that I can say that that's the same as A or B. I'll take the brackets and I intersect that with A or C. Okay, and again, you don't have to copy this down. It's exactly what you see in 7. I'm just trying to say that basically I can take A, I take its union, and I can put that together with B, and I get this thing here. And I can take A, I can take its union, and I can put it together with C, I can put it there, and then I put the intersection there. And this is called distributivity. Okay, it's a distribution law for those of you who studied pure maths. Okay, and you can do that exactly the same with the intersection side. So again, what I wrote on the board, no need on the transparency. It's the same if I flip now. So here, if I look at this equation, which I've explained to you as just being a rule, it's the same as on the line below is identical, except I flipped the union here and I flipped the intersection, and here I flipped the union in the intersection, I flipped the union in the intersection, I flipped the union in the intersection. So the distributivity law says that basically it doesn't matter if I've got U's or cups, if you like, I can use this rule however I like. Okay, so that's 8, and so we have two kind of tricks. They're nice tricks which we're going to use at some stage, I hope. Number 9, it basically says if I take A or B, that's the same as taking A or B and A complement. Okay. So let's have a look. Let's think about this one, because this is one which I can do on my diagrams. Okay, so let me just try to explain. So I'm talking about property 9 of page 35. So what I'm going to try and do is to try to give you some understanding of why that's the case. So I take my sample space S. Okay, S is what I tried to write down. This is supposed to be some sort of square. And I take A, which is on my left like this. And I take my set B, and they're nice and disjoint. Okay, so now the operation so the left-hand side of that equation 9. So hopefully you have the lecture notes, but if you don't know what I'm talking about, or if you've stopped listening, let me just remind you. First of all, let's think about what this left-hand side is. This left-hand side is A or B. Okay, so now if I go back to my plot, oh dear God. Okay, A or B. So A union B is just this shaded region. Okay, so that's the left-hand side of the equation. Now let's think about the right-hand side of the equation. So this is A union B. So I don't know if you can see any of these things. This is A union B. Okay, sorry. That's A union B. That's the left-hand side of equation 9. Let's think about the right-hand side. So the right-hand says something else. So now I'm going to draw something which is supposed to look very much like the top. I'm sorry that they're not on top of each other. So that if you are interested in copying it down, this is just simply says A union B. This thing on my right says S. This is a square. This is supposed to be A. This is supposed to be B. And they're supposed to be shaded. Okay. So that was the left-hand side of A union B. Now the right-hand side of this property 9 on page 35 says I take A union B intersection A complement. Okay, so that looks very complicated. So first of all, we write down the set A. Okay, so this is the set A. Okay, now that's union with B and A complement. Okay, so that's the set A. Now what's A complement first of all? Well, A complement is everything which is not shaded in this box. Okay, and so that's A complement, and I want to intersect that with B. So if I intersect the complement of A with B, what I get is basically this is supposed to be B. Okay, this is B. So this thing here, this B, is precisely B intersection A complement. This is my example. This is not a proof. I'm trying to illustrate why 9 is true. So this thing, on what I've written through my logic, is A union B intersection A complement. Okay, and that thing is identical to this one here. Okay, this is an example of why it's true. It's not a proof. Okay, I'm just trying to help you understand why 9 would be true. You can, again, we don't prove these things. They're not important to prove. Okay, very good. So that's that. So let's so again, basically, again, if you really wanted to copy it down, it was just basically a rectangle with 2 circles colored in. One says A, one says B. So the last one, this is a nice trick. You can use a similar logic to establish that A, this is a very nice trick, that if you take A, that's the same as taking A and everything in B, or A and everything in B complement. And it's kind of clear, like, let's think about this a little bit clearly. Why is this the case, right? What does this thing mean on the right-hand side, this equation? So it's my right, it's your right as well. So A intersection B, what it means is everything in A and simultaneously in B. Okay. What this thing means is everything that's A and everything which is in B complement. Okay. Now, if you add those two together, at the end of the day, you're going to get A. Okay. If you prefer, you can try and use these rules to prove it's true. It's also very simple to do that, but I think that this is not a course for proofs. Okay, so I don't prove anything. I'm happy to do it, but I've done that before. People start crying, so I don't do it. Okay, very good. So let's move on. So there are a couple of rules again. These ones are called De Morgan's law. There's a law for a reason, because we're not going to study the proof. So this is basically just looking at those unions and intersections. So this thing, remember, let's just remind ourselves, what do these things mean before we go on, because it's important to understand what we did already. I keep going the wrong way. So remember that remember this thing we talked about a few moments ago, this big cup UAI. So what this is, the union of n sets. So that is the selection of X such that X belongs to one of A1 up to AN. Okay, that's what this thing means. Right, very good. So now the De Morgan law says, if I take this union, right, and I take the complement of this union, so I take the union which is every element X which belongs to this union belongs to at least one of A up to AN, and I take the complement of that, that's the same as taking the intersection of these n sets. Okay, it's a rule. You can take it as a rule if you like. It's basically the generalization of this one here. So remember property 6, which I just said was a property. If you like, you can establish these things. This is the case n is 2. Here I'm using A1 is equal to A, A2 is equal to B. Okay. This one is just a generalization. So if you like, you needn't have understood that property 6. You could just at least know this property 1 on this page. And again, the thing is the same when you do the intersections. So I take a finite intersection or countable intersection A1 up to AN. So that means if I take an element belongs to this collection, this set on the left-hand side, if X simultaneously belongs to A1, A2 up to AN. Now if I take the complement of that set, that's the same as taking the union of all these sets, which is the complement A1 complement union A2 complement union AN complement. And that's just a generalization of this one in the case n is equal to 2, A1 is equal to A, A2 is equal to B. Okay? And these are going to rules, we're going to use them. Okay, so I know this is a little bit dry, but we're going to use these things along the way. So let's have a look at some examples. So these examples are the following. So we have 10 minutes left, and we're going to try and do these to reinforce what we've learned today. So we go back to our first example of this course, rolling a dice. I have the sample space 1, 2, 3, 4, 5, 6, and then we along the way added the example where we have 3 sets A, B, and C, which are as such. Okay? Okay, so we know some things. We know what the complement of A is, because the complement of A, I get 1, 2, 3, so the complement of that is of course 4, 5, and 6. And again, I can compute the complement of B. So the complement of B is going to be 2, 4, 6, and similarly the same for C. The complement of C of 2, 4, 6 is 1, 3, 5. Okay, and what are we going to do? Well, I'm just going to illustrate that these laws happen to hold true, these De Morgan's laws happen to hold true in this example. Yeah, it's not a proof, it just says, well, they happen to hold true here, and they happen to hold true in general. So now, De Morgan's law number 1 says I take the union of n sets and I take the complement. That's the same as taking the n-fold intersection of those complements. Okay, so what that says, let's look at the left-hand side of De Morgan's law. So A union B union C, what does it mean? First of all, that's 1, 2, 3, or 1, 3, 5, or 2, 4, 6. Well, the union of these 3 sets is 1, 2, 3, 4, 5, 6. So now if I take the complement, this dash is here, the complement of the sample space is the empty set. Okay, so what does that say? That says that the left-hand side of De Morgan's law in this example is precisely the empty set. Now let's verify that the right-hand side is equal to the left-hand side, as if we didn't know that would be the case from the beginning. So so in order to do that, we want to first of all compute A complement, B complement, and C complement, and we've happened to have done that at the top of the slide. Okay, so now, so in order to work out the intersection, we want to work out all the elements which belong simultaneously to A, B, and C complement respectively. Okay, so if I look in these elements, so basically I'm going to get 4, 5, or 6, 2, 4, or 6, 1, 3, or 5. So there's no element which belongs simultaneously to this set, set, and this set. Therefore, A complement intersection, B complement intersection, C complement is precisely the empty set, and that's as we expect it precisely from De Morgan's law. Okay, so let's have a look at our second example. So the second example is basically the other form of De Morgan's law. So let's just see, just bear with me, it's just a few more minutes. Okay, so the second form of De Morgan's law, I take a finite countable intersection of sets A1 up to AN, and I take its complement, and that's the same as the countable union of the complements. Okay, that's what it says in words. So let's have a look at the example. So of course we start with the left-hand side, so we take A, B, and C. They're the same sets as before, so the complements are the same. So this line and this line is identical to the one that we've just discussed. So now if I ask the question, what's A intersection B intersection C? Well, we already worked that out. That was this thing, and that happened to be the sample space. Oh, sorry. A intersection B intersection C. So if I look at this, well, again, that's, yes, it's empty. So the complement, this set is empty. So the complement of the empty set is the sample space. Okay. On the other hand, the right-hand side of the De Morgan's law says you take A complement union B complement union C complement. Okay, so I take this one union this one union this one, so I take this one union this one, this union this one. So I think of all of these sets, all of these elements, I add all the elements, so I get a 4, I get a 5, I get a 6, I add on a 2, I add on a 1 and a 3, and I get added of and I get the sample space. Okay, so again the left hand side is equal precisely to the right hand side. Okay, we've got time. Okay, so let's have a look one last thing to kind of soldier through before we go we finish the lectures. So look, we take one final operation, which is called the contained operation. So the contained operation, is the following. So I have two sets, events A and B, sets if you like. So A is said to contained in B, and it's a notation like this. If we have the following, is if we take every element in A, it also belongs to B at the same time. Okay, so what does it mean? So let's see just one final example on the telestrator. Okay, so unfortunately the telestrator is not working again. So A contained in B, what that means is you can have the sample space, you take B, and A is a set which lies within A. So if I take a point in A, it has to belong to B. Okay, but B may contain elements which don't belong to A. So a key remark to this is if A is contained in B and B is contained in A, it must be the case that A and B are the same, otherwise it cannot be the case. Okay. Okay, let's have a look at an example, a lot of examples. Let's just have a look at one example. I don't think we'll get through. Well, let's see what we can do. We've got 4 minutes. Okay, so let's look one last example for sure. So if we flip a die, we roll a die, and then we flip a coin. If the number on the die is even, we flip it, this is a silly example. So we roll a die and then flip a coin. If the number on the die is even, and otherwise we flip the coin twice if the number is odd. Okay, so I roll my dice. If I get a 2, 4, and a 6, 2, 4, or a 6, then I flip a coin, and if the number on the die is odd, then I just flip the coin twice. So all the possible outcomes in this rather confusing experiment are the following. So here, what I did is I rolled a 1, so then I have to flip my coin twice. And similarly, I do it here. I rolled a 1, I flip a coin twice, I get a head or a tail. I rolled a 1, I got a tail and a head, and so on and so forth. In this scenario, what I did is I rolled a 2, that's even, so now I just flip my coin and I can get a head or a tail, and I repeat that as many times as you like. So let's introduce an event, A, which is the number shown on the die is less than 3. Okay, so this is what? Well, this event is basically going to be this one, this one, this one, this one, this one, and this one. Okay, so that's the set A. The set B is 2 tails occur. Well, this is slightly more complicated because I get this one, and I get this one, and I think I get this one. Okay, so I only have 3 elements of this event. And then this one says even numbers shown on the die. So that's again a 2, 4, or 6. Okay. Those are my 3 events. Okay. And I can compute the complement. I don't know why I want to compute the complement, but I do compute the complement. What does this mean? Well, the complement of A is I look at this set, I remove these 6 elements, and I'll get A complement. And if you do that, it's going to take us a long time. You would get that. Similarly, B complement, I take this set, all these elements, and I remove these 3, and I'll get B complement. And you can do the same for C. Okay, I'm not going to do that. We can also think about A intersection B. What is A intersection B? Well, I look at this is my set A. This is my set B. Now, which elements belong to A and B simultaneously? Well, I can see this one does, and that's the only one. Okay. Similarly, I can take A intersection C, so it's the same operation. So I look at all these, and I look at all of these, and I look at where the common events. This one is common, this one is common, and that looks like that's it. So I get two elements there. B intersection C is apparently empty. Where is that? So B, if I look at B, that does not occur with C, so that's empty. And you can do the same thing a few more times over. Let me see, what time do I have? We'll cover these events tomorrow. I don't think we'll have time to do it today. Okay, so that's it for lecture 1. It's pretty much like this for the first chapter. There's not much probability yet. Thanks very much for your attention. I'll see you tomorrow at 2 o'clock in LT28.